This is a 6-area OSPF network build for a defense contractor. Every area boundary exists for a reason. Function, geography, line of business, head end, cloud. By the end of this video, you'll understand why each of these boundaries exists. You'll prove every one of them in Wireshark, and you'll watch me add and remove a site without touching the rest of the network. Let's get into it. Let's talk about why multi-area OSPF exists. Because if you're going to design it, you need to understand the problem it solves. In a flat, single-area OSPF network, every router floods every LSA to every other router. One link flaps anywhere in the network, SPF runs everywhere. Every router, all at once. At 10 routers, that's manageable. Barely even noticeable. At 50 routers, it's chaos. You've got routers spending CPU time reconverging for changes that have nothing to do with their part of the network. Now take Meridian Defense Systems. They've got an East Coast headquarters, engineering, admin, IT. They have a West Coast facility, manufacturing, test labs, isolated program enclaves with separate contracts and separate change control, remote field offices terminating through a WAN head end, and even Gov Cloud connectivity for external services. Right now, all of that is sitting in one OSPF area, one flat domain. Every change in every corner of the network hits every router. That's a problem. We're going to fix that area by area, and I'm going to prove each design decision inside Wireshark. Let's start with the backbone, Area 0. This is the foundation. Everything else connects through here. R1 and R2 are the backbone for. These routers already have their configs loaded, so let me walk you through what's on them and why it matters. The first command I'm going to run, and the most significant, is show IP OSPF interface brief. This is the command I want you to remember. It shows you every OSPF enabled interface, which area it's in, and its state, all in one view. Every interface on router 1 is in area 0. Gig 00 connects to R2. 01 and 02 connect to the area 1 area border routers. 03 connects to the area 3 area border router, and 04 connects to the area 4 area border router, all area 0. Router 1 is a pure backbone router. It does not participate in any other area. Now let me show you the OSPF process config. The command that I want you to pay attention to is show running config, or a show run, and then we will do a pipe section router, which we will have to spell out, OSPF. Router OSPF process 1. The router ID is 10.0.0.1. That matches loopback 0. Every network statement is explicitly in area 0. That's intentional. Router 1's only job is backbone transit. So now let's go ahead and confirm adjacencies. I'll open this up, show IP OSPF. We have 5 routers. Router 2, router 3, router 4, router 9, and router 11. All full. Router 1 is the hub of area 0. Every area border router in the network connects through here or through router 2. Now let's open up Wireshark to display a router 1 to router 2 link. Right now, as we can see, and we'll make it a little easier to filter for OSPF, the only thing that we can see are hello packets. They occur every 10 seconds by default. That's OSPF maintaining the adjacency. I'm still here. Are you still there? And that's it. Nothing else. The network is stable, so there's nothing to flood. Let me force a change so you can see what OSPF actually does when something happens. So what we'll do is we'll head back to router 1. We will clear IP OSPF process. And as you can see, I'm tabbing quite a bit here. And the default answer is no. We will type yes. And then we will go ahead, reopen Wireshark. Now watch. The adjacency is reforming. You'll see database description packets. Let me open this up. As we can see here, that's router 1 and router 2 negotiating who sends first. The link state request and link state update packets. Inside those updates, and we will go ahead and expand 1, you'll see LSA headers with LS type 1, as we can see here. That's a router link state advertisement. Router 1 is advertising itself. Router 2 advertising itself as well. Intra-area topology. This is the backbone working. Once it settles, we're back to just hellos. All quiet again. That's a healthy OSPF network. Noisy when something changes, silent when it's stable. These two routers are the backbone. Their only job is transit. No end users, no servers, no services. Just moving inter-area traffic between everything else. That's the function criteria. Area 0 exists because of what it does, not where it is, and not who uses it. Now the East Coast headquarters. This is where engineering and admin live. Area 1. Router 3 and Router 4 are our ABRs for this area. Each of them has interfaces inside Area 0 and interfaces in Area 1. The dual area presence is exactly what makes them area border routers. Router 5 is a purely internal router. It only lives inside Area 1. This is where the real teaching starts. Let me show you what makes an area border router an area border router. And to do that, we'll open up R3. Inside of R3, I'll type show IP OSPF interface brief. This is the key. Look at the area column. Gig 0, 0 is area 0. That's the backbone link towards router 1. Gig 0, 1, area 1, that's the link to router 5. And gig 0, 2, area 1, that's the link to router 4 for area border router redundancy. One router, 2 areas, that's an area border router. Now let's look at the OSPF config. So to do that again, I'll do a show run, pipe section, router, OSPF. See the network statements? 2 are in area 0 and 2 are in area 1. That's what puts R3 in both areas. The router ID is 10.0.0.3, which also matches loopback 0. Let's confirm router 3 actually knows it's an ABR. So if we do a show IP OSPF, this will actually say it explicitly. There, iOS says it directly. It is an area border router. 2 areas are listed, but that's router 3 confirming its own role. Now let's take a look at router 5, which is an internal router, as we just discussed. This is where it gets interesting. So on router 5, we will type a show IP OSPF interface brief. Every interface on router 5 is in area 1. Nothing in area 0. Router 5 is internal. It has no idea the backbone even exists as a topology. It just knows that router 3 and router 4 can get it there. Router 5 also has 2 loopback interfaces, 172.161.0/24 and 2.0/24. These are simulated local area networks. They give us real prefixes to verify inter-area reachability later. Now, here's the most important comparison in this entire video. If we type show IP OSPF database. We can look and see that the router link state section, you only see area 1 entries. Router 3, router 4, and router 5. That's it. No router 1, no router 2, no router 6, 7, or 8, or any other router in the network. Now let's go ahead and we will look at the summary net link states section. These are known as Type 3 LSAs, which we have discussed in previous videos. And look at the advertising router column. We can see 03 and 04. The area border routers. Only the area border routers. Router 5 doesn't see area 0's topology. No Type 1 router LSAs from router 1 or router 2, just summaries. Prefixes and costs. That's the whole point of multi-area internal routers are shielded from everything outside of their area. So let's compare that to router 3. So in router 3, we'll go ahead and type the same command, show IP OSPF database. Router 3's database is much bigger. It has entries for both areas. Type 1 LSAs from area 0, Type 1 LSAs from area 1, summary LSAs going through in both directions. And because the area border router carries the full picture, the internal router only carries its piece. So as we can see here, area 0 and area 1 are in this database. Let's prove this in Wireshark. I'll capture the router 3 to our router 1 backbone link and force router 3 to reflood so we can see the LSAs across the boundary. So back in GNS3, we'll go ahead and open up a Wireshark capture between router 3 and router 1. And before anything, we'll go ahead and do a filter for OSPF. As we can see now, we just have hellos as we expect, which indicates a stable network. So on router 3, we'll go ahead and we will type clear IP OSPF process. And we will indicate yes. And then we will come back to Wireshark. Now watch. The adjacency reforms, and then there. Link state update packet. So let's take this update packet for that matter. We'll expand OSPF. Look at the LSA headers inside. You'll see LSA type 3 right here, which is our summary LSA. And we see a lot of those. Look at the advertising router field. If we go ahead and expand one, our advertising router is 10.0.0.3. That's router 3. And the link state ID, that's an area 1 prefix. R3 is taking the topology from area 1 and advertising just the prefixes into area 0. No topology detail, no router link performance, just here's a prefix, here's the cost to get to me, and that's the summary. That's geography. East Coast headquarters gets its own total area. How about our West Coast facility, manufacturing, test labs? Same pattern, geography. However, area 2. Router 6 and router 7 are the area border routers, similar to what we had in area 1. Router 8 is the internal router, same structure as area 1, but different region. So now let's hop into router 6's terminal. And what we'll do here is we will do a show IP OSPF interface brief as we did on the other routers. So we have the same pattern as router 3, gig 00 in area 0, connecting to router 2 on the backbone, gig 01 area 2 connecting to router 8, and gig 02 area 2 connecting to router 7 for area border router redundancy. One router, 2 areas, ABR. So now we will do a show IP OSPF neighbor. Neighbors we have here in both areas. Router 2 is in area 0. Router 7 and 8 and area 2 all are full. Now let's do a Wireshark comparison. two captures, two different perspectives on the same boundary, and this is how you prove the boundary is doing its job. I'm going to start captures on two links at the same time. The router 6 to router 8 link, that's inside area 2, and the router 6 to router 2 link, that's the backbone side. Then I'll clear OSPF on router 6 so both captures see the same event. So now that I have my captures up side by side, let's go ahead to router 6 and we will do a clear IP OSPF process. We will select yes. And now what we're going to do is transition to the router 6 to router 8 link. I know it's a little bit difficult to see. Watch the link first. This is inside area 2. So our filter is just OSPF. You can see the adjacency reform and the link state update packets. So if we take an update packet, as we can see here, and we go ahead and expand it, we'll expand both here to the best of our ability. We'll actually decrease this one. We look at the LS type field and the LSA header. All right, so we can see it is type 1. This is a router LSA. That's router 6 and router 8 advertising their links to each other. Full topology detail, every interface, every neighbor, every cost. This is the complete link state picture inside of the area. Now if we go to the router 6 to router 2 link, the same, we have OSPF filtered, same event. Router 6 cleared its process. But look at what came across this link. So let's take an update here. Go ahead and shrink this. We'll expand OSPF, then we'll expand our LSA. The LS type field says 3, as indicated here. Summary LSA, not type 1. Router 6 is not flooding area 2's router to router topology into area 0. It's summarizing it, prefix by prefix. Just the destination and the cost. Same router, same moment, different LSA types on each link. That's the area border router doing its job. West Coast stays West Coast. Now we will talk about area 3. This one's different. Area 3 is an isolated program enclave. Separate contracts, separate teams, separate change control. These guys don't want their changes in their area triggered reconvergence anywhere else, and the rest of the network doesn't need to know their topology either. Notice something. We only have one area border router here. Router 9. Not 2. That's intentional. This program doesn't need redundant area border routers. It needs isolation. A second area ABR would give them another path in, and that's not what the design calls for. So let's go to the router 9 terminal. In this terminal, we will type show IP OSPF interface brief. So we see gig 00 area 0 connecting to R1. Gig 01 is area 3, and that is connecting to R10. 2 areas, 1 ABR, simple and intentional. So now if we do a show run section router OSPF, 1 network statement in area 0 and 1 in area 3. Single point of entry into the enclave. That's their design. So now if we do a show IP OSPF neighbor, 2 neighbors, router 1 in area 0, router 10 in area 3, full. Let's look at router 10's database. So now if we do a show IP OSPF database, by now you should start seeing a pattern in these commands. Only 2 routers in area 3, router 9 and router 10, as we can see here. The router link states section is tiny. The summary net link states all come from one advertising router, and that is router 9, which we can see here. Because router 9 is the only area border router. Compare this to router 5's database from area 1. Router 5 had more router LSAs, more summary LSAs, because area 1 has more routers and 2 area border routers. Router 10's world is smaller by design. Router 10 has no idea what the West Coast topology looks like internally, because it doesn't need to. Giving this program its own area means a config change here never triggers SPF anywhere else. A new router in Area 3 doesn't cause reconvergence in Area 1 or Area 2. The blast radius is contained, if you will. Line of business, that's Area 3. Let's now look at Area 4. Area 4 is the WAN aggregation point. Every remote field office terminates here through router 11. This is the common head-end criteria. All remote sites share this aggregation point. So now if we head over to router 11 and we conduct the show IP OSPF interface brief, we have gig 00, which is area 0, connecting to R1 on the backbone, gig 01, area 4, connecting to R12, and gig 02, area 4, but no neighbor yet. That interface is waiting for our new site. We'll come back to that. So now let's do a show IP OSPF neighbor. Two neighbors right now. Router 1 in area 0, router 12 in area 4. Both are full. Before we move on, I want to start a Wireshark capture on this link right now. So what we'll do is here in between router 11 and router 12, we'll go ahead and start a capture. We will expand it so you can fully see it. And we will filter for OSPF. Right now, you'll just see hello packets every 10 seconds, but in a few minutes, we're going to add a brand new site right here. And I want you to see exactly what the rest of the network does or doesn't do when that happens. So remember this capture. We're going to come back to it. It's a common head end, which is area 4. But right now, we just have hello packets, indication of a very stable network. So now we'll head back over to GNS3, and we'll talk area 5. The last area, area 5, GovCloud connectivity. This one's special. GovCloud routes are external to our OSPF domain. They're not part of our internal network. Their prefixes we're learning from a cloud partner redistributing into OSPF. That makes them a Type 5 external LSA by default. But here's the problem. Type 5 LSAs flood everywhere. Every router in every area sees them. For a handful of GovCloud prefixes, that's a lot of unnecessary flooding. The solution is NSSA, or not so stubby area. Instead of Type 5, NSSA generates Type 7 LSAs. They stay contained within the area. The area border router converts them to Type 5 only when forwarding them to the backbone, and only selectively. So we'll head over to router 13's terminal, and we will do a show run section router OSPF. This is where the config gets interesting. Two things to point out. First, area 5 NSSA. That single command is what makes this area an NSSA. Without it, any redistributed routes would generate Type 5 LSAs that flood the entire domain. Second, we can see redistribute static subnets. That pulls into two static routes, 192.168.100.0/24 and .101.0/24, both pointed at null 0. Those simulate a GovCloud prefix we're learning from the cloud provider. So let's see the actual result. So if we do a show IP OSPF database and then add NSSA external, we could see Type 7 external link states in area 5. These describe the GovCloud prefixes, and they stay in area 5. Other internal areas would never see these LSAs directly. So now let's show you this in Wireshark. I'll capture the router 13 to router 2 link, and then we'll clear the OSPF on router 13. So we'll head back to GNS3. We'll go ahead and start a Wireshark capture between router 13 and router 2. Now we'll go ahead and filter for OSPF. Now back on router 13, we will clear IP OSPF process. We'll type yes and go back to our Wireshark capture. Watch the link state updates come through. So let's go ahead and we will pick an update. Here we see LSA type 5. Now, if you notice the distinction here, the rest of these messages were sent to a multicast destination. The difference here is on this LS update, we have unicast to unicast. Here we see our LSA type 5. That's router 13 acting as the area border router, translating the type 7 NSSA externals into type 5 AS external LSAs for the backbone. So the raw type 7 stay away, or they stay inside area 5. What crosses this boundary is the translated type 5, the clean version the rest of the network can actually use. If you want to see only the external LSAs, you can actually scroll through the link state updates for LS type 5 and the LSA headers. The link state ID will show you 192.168.100.0 and 101, which is our GovCloud prefixes. And as you can see, we have that here and here. Now let's check the routing table on router 1 in the backbone, because as we saw before, router 1 is our backbone router. So here, we will do a show IP route, OSPF only. And what we're looking for here is those GovCloud routes. And as we can see, they are here. They show up as N2, OSPF external type 2. Learn through NSSA. The backbone knows about them, but internal areas like Area 1 and Area 2 didn't have to process the full Type 7 flooding. And that eases the processing power that's going to be needed in order to handle this convergence. Now, all 6 areas are up. Let me show you the full picture before we start messing with things. If we head to R1, and we go ahead and show, we'll open it up first, and we will do a show IP OSPF database. R1 is the backbone. It sees entries from every single area. Summary LSAs coming in from every area border router. This is the most complete view of the network. Now, if we go to router 5 and we do a show IP OSPF database, router 5 is an internal router in area 1. So if we compare that entry count, it's much smaller. Router 5 sees area 1's full topology, the type 1 router LSAs, and then summaries for everything else. It doesn't need to know about the West Coast topology or the program enclave internals. It just needs to know how to get there. So if we actually did a show IP route OSPF, 3 types of OSPF routes here. O is intra-area. Learn from type 1 and type 2 LSAs within area 1. Then we have O, IA, or inter-area. Those came from type 3 summary LSAs from the area border routers. And then lastly, we have our ON2, and these are the GovCloud external routes learned through NSSA. So now, if we wanted to verify that, we could go ahead and we could ping 10.0.0.12, and then we'll source it from ourselves. And as we can see, that's a success, which is router 5 to router 12 in area 4. Now let's go ahead and ping router 10. And we can see router 5 to area 10 and area 3 is also a success. So we have full reachability across all 6 areas. The network is working. So now let's stress it. So what we're going to do here is head back to GNS3. And right now, to simulate adding a route, I've actually gone ahead and suspended this link. And by suspending it, it means that it doesn't exist just yet. So what we're going to do is I'm going to start by conducting a Wireshark capture on 2 links. So we'll do between router 1 and router 2, and between router 4 and router 5, and then we will filter for OSPF. Okay, so we have those captures ready. So now what we'll do is real quick, I will go to router 14, and I will do a show run section router OSPF. And as we can see here, we are in the process. We do have a router ID and a few network statements that are in area 4 and area 4 only. Okay, so now from here, what we're going to do in GNS3 is unsuspend that link. So I'll go ahead and resume this link, go back to our captures, and now we'll go to router 11's terminal, which is our backbone. So what we can see here is that we have a neighbor state for router 14 now. So the new site is up, and we can see that right here. Now, right now it's in our two-way, but if we give it a minute, we should be able to get to a full state. But now what we're going to do is we'll look at our capture between router 1 and router 2, which we can see here, and we have the update packets, and we have the update packets appeared on the backbone. These weren't here before, so if we go ahead and expand one, and we look at the LSA header, we should see type 3 from our area border router. We have an LSA type of 3, which is our summary LSA, and the advertising router should be 10.0.0.11, which is router 11. Router 11 is the area border router for area 4, and it's telling the backbone there's a new prefix reachable through me. That backbone sees the new site. So now if we go to area 1, which is our router 4 to router 5 capture, do we have anything here? We may actually expect silence to be here, but in essence, area 1 did get an update. You'll see the link state update packets from router 4, and I have one expanded here. What we can see here is an LSA type 3, which is our summary LSA, and our advertising router is in fact router 4, the area border router. Here's what happened. Router 11 sent a type 3 into the backbone, router 4 received it on its area 0 interface, and then router 4 generated its own type 3 into area 1 saying, there's a new prefix and I can get you there. Area 1 did see the update. If we go back over to router 5 and look at its OSPF database, we can see the link states in area 1. Clear as day. Same as before. Router 3, router 4, and router 5. No router 14. Router 5 has no type 1 router LSA from router 14. It has no idea router 14 even exists as a router. It doesn't know router 14's interfaces, its links, or its neighbors. Now, if we look at these summary net link states, there's new entries and router 14's prefixes, which we can see here, and advertised by router 3 and router 4. These are type 3 summaries. Just a prefix and a cost, that's it. In a flat single area network, router 5 would have received router 14's full type 1 router LSA. Every interface, every link, and every cost. Router 5 would have run a complete shortest path first recalculation across the entire topology. At 50 routers, that's expensive. At 200, that's crippling. Instead, router 5 got a type 3 summary. It's updated its routing table with a new inter-area route. Its intra-area SPF tree, the part that actually matters for forwarding traffic inside of area 1, didn't change at all. That's the difference. It's not silence, it's surgical precision. Area 1 learned about the new site through a lightweight summary, not a full topology flood. Let's head back to our GNS3 topology and let's go the other direction. What happens when we lose a site? So what I'm going to do now is have the same setup, but we'll have 2 Wireshark captures running before I change anything. We'll do router 6 to router 2. That's the Area 2 AVR linked to the backbone, and we'll filter for OSPF. Then we'll do router 4 to router 5 inside of Area 1, same filter, both showing hellos right now. All right, so we have our router 4 to router 5 captured and router 6 to router 2. And as we can see, we don't have anything out of the ordinary when it comes to OSPF. We have our general hello statements and acknowledgements, and dead timers, and regular day, regular traffic, if you will. So we're about to give it its bad day. What we're going to do is we're going to shut down router 8. So the way that we're going to do this is shut down both of our links. We'll go ahead and suspend our link here, and we will suspend our link here. So router 8 is now shut down. So now if we come back to our captures and we look at our router 6 to router 2 link, we can see there's new link state updates. So what we're going to be looking for is an LSA with an LS age set to 3600. We should have that max age. So what we'll do is we'll take our LSA here, and then as you can see here, it's set to 3600. That's our max age. That's OSPF saying this LSA is being withdrawn. The routes through router 8 are gone. Router 6 is updating the backbone with new Type 3 summary LSAs reflecting the change. SPF ran in Area 2 and in Area 0. Now Area 1. Same thing we saw with the add. Router 4 sends updated Type 3 summary LSA into Area 1, reflecting the withdrawn routes. Area 1 sees the update, but it's the same story, just summary updates. No Type 1 topology changes. Router 5's intra-area SPF tree is untouched. So let's confirm that on Router 5. So on Router 5, we'll go ahead and execute the same command. So again, Router 5 link states in Area 1 remain unchanged. So if we come up here, Area 1, our link states have not changed. We still have routers 3, 4, and 5. Area 1's topology didn't move. The summary netlink states updated. Router 8's prefixes are gone, as we can see here. Router 5 never knew Router 8 existed as a router. It just knew Router 8's prefixes were reachable through Router 3 and through Router 4. Now they're not. In a flat single area network, Router 8 going offline would have triggered a full SPF recalculation on every router in the network, including Router 5. Router 5 would have had to process the topology change, remove Router 8's Type 1 LSA, and rebuild its entire shortest path tree. That's expensive at scale. Here, Router 5 just removed a few inter-area routers from its table. Its SPF tree, the intra-area topology that drives actual packet forwarding inside of Area 1, never changed. That's the power of proper area design, but you can see how taxing and critical it can be to make it right. The topology change was in Area 2. The SPF recalculation stayed in Area 2. Every other area got a lightweight summary update, not a flood. So let's walk through what we built. Area 0 function, the backbone. Its only job is to transit. No end users, no services, just moving traffic between areas. Areas 1 and 2, geography. East Coast and West Coast, they're separate areas because they're separate physical locations with separate operational needs. Area 3, which is our line of business, an isolated program enclave. Separate contract, separate change control, a single area border router because isolation was the goal and not redundancy. Area 4, our common head end, all remote sites terminate here. One aggregation point, one area, clean and consistent. Area 5, our cloud service provider, GovCloud connectivity through an NSSA so external route flooding stays contained. Every area boundary has a function. That's not theory. You just watched it work. You watched a new site come online in Area 4 and saw Area 1 get a lightweight summary, not a topology flip. You watched site go offline in Area 2, and then you saw Router 5's intra-area SPF tree stay completely untouched. That's what the area design looks like. Not zero communication between areas. That's not how OSPF works. But control, summarized communication. Every area knows what it needs to reach without knowing every other area is wired internally. One more thing. We walked through 14 routers today. At 50 sites, you'd add route summarization at the ADRs to shrink routing tables even further. You'd convert some of them into stub areas or stub routers to cut down flooding, and you'd automate the configuration so you're not hand typing every site, which can obviously mess you up if you do it wrong. But the design principles are exactly the same. Cloud, function, line of business, head end. Start there, the tooling follows. Lab configs are in the description. All 14 routers. Build it yourself. Break it, fix it. That's how this sticks. If this helped, hit the like button. Drop a comment if you've got questions or if you want to see the summarization and stub area follow-up. And I'll see you in the next one.